Hi everyone, in this session we are going to learn about Kirchoff's current law, which is known as KCL. First, let us take a circuit. It contains a voltage source which has two terminals, positive and negative. That means one terminal is at more potential compared to the other terminal. That means the negative terminal contains more number of electrons. Suppose two elements are connected like this, okay? These two elements are connected like this. Whenever more than one circuit element is connected, that is known as junction. This is a junction here, this is a junction here, okay? A voltage source is connected, so definitely electron flow and current will be flowing. And similarly, these resistors are going to act as a loads, so they consume current. I am taking I1 as the current consumed by resistance R1, I2 is the current consumed by resistance R2. What Kirchoff current law says is the algebraic sum of currents. Algebraic means with a sign. At a junction, if you assume that entering current is positive, the leaving current you should treat it as a negative. So the algebraic sum of currents is 0. Okay. Here if I apply this one, it will be, I am taking the entering current as positive, that means the I as positive, then the leaving currents from this junction are I1 and I2 should be treated as negative. So I is nothing but I1 plus I2. The another way of treating this Kirchoff current law is the sum of current entering a junction is nothing but sum of the currents leaving the junction. The sum of the currents entering the junction is equal to sum of the currents leaving the junction. Okay. V1, I1 is nothing but the current flowing through resistance R1. Same voltage is applied across both the resistors. If you see, these two resistances are having two common junction points. The current coming here will pass through both the resistors by dividing and will join here and flow back to the source. Here for the current only one entry point, one exit point is there. These two elements are having two junctions as common and no other element is connected there. Then these two are said to be connected in parallel. Here if you see, same voltage source is applied across each and every resistance. Okay. So that means voltage across R1 is Vs, voltage across R2 is Vs. If I substitute this one, similarly if I represent this as this resistance combination as what equivalent resistance, which is I am representing as R equivalent, then current I is nothing but Vs by R equivalent. If I substitute that one, if I take Vs as common, so R equivalent is nothing but 1 by R1 plus 1 by R2. This is nothing but, if I take R1, R2 as common, this is nothing but R1 plus R2, which is nothing but R1, R2 by R1 plus R2. That means if two resistances are connected in parallel, the equivalent resistance is nothing but this equation R1, R2 by R1 plus R2. Next, we are going to derive the current in each branch in terms of the total current delivered by the source. I1 if I take, it is nothing but Vs by R1. Vs is nothing but I into R equivalent by R1. If I substitute R equivalent as this formula, it is nothing but it is nothing but the current in the branch 1, that is in resistor R1, is I1, which is nothing but total current into resistance in the other branch by sum of the resistances in the two branches. Suppose similarly you can derive I2 as Vs by R2. If you substitute Vs as IR equivalent and everything, you are going to get I into R1 by R1 plus R2. Let us extrapolate this to suppose n elements are connected. This is Rn. For n elements, if you connect, the current in first resistor, that is R1, is nothing but total current into suppose so many elements, n elements are connected. The current in a particular branch is total current into what is the equivalent resistance of all other branches excluding this branch by this branch resistance plus equivalent resistance of all other branches excluding this branch. Similarly, we can extrapolate to any other branch and you can derive the similar formula. Suppose if it is for R2, it is nothing but I2 is nothing but I into all the branches equivalent resistance excluding R2, R1 in parallel with R3 up to Rn by R2 plus R1 in parallel with R3 up to Rn. What is the equivalent resistance? Similarly, you can derive for current in any other branch. Next, I am taking an example to explain the current in each and every branch. Here we have to find what is the total current, what is the current in 3 ohms, current in 6 ohms. If we get currents, we can get voltages also. First, I am trying to find the equivalent resistance. These two are connected in parallel, okay, because two junctions are there. At that junctions, no other element is connected. The equivalent resistance is nothing but R1 into R2 by R1 plus R2. It is nothing but it is 2 ohms. So total current I is nothing but Vs by R equivalent. It is 5 amperes. Current in 3 ohms, that is I1. I1 is nothing but total current into other branch resistance by sum of these two. It is 9. It will be 3.33 amperes. Then if I1 is like this, V1 V1 is I1 into R1. I1 is 3.33 into R1 is 3 ohms. Then it will be 10 volts. Okay. Next I2 is nothing but total current 5 amperes into resistance in other branch 3 ohms by sum of resistances. It is 9. It is 15 by 9. It will be 1.67 amperes. Similarly, if you find V2, it will be I2 into R2. R2 here is 6 ohms. So 1.67, it will be 10 volts. Okay. As these two are connected in parallel, we are going to get the voltage across each resistance same as the source. In other examples, you may get different. If some other resistance in between the source and these resistances, you may get different voltage across each and every resistance. Thank you. In the next session, we will learn about KVL.